Okay. All right. Well, it's good to see you all on week 7, and so yeah, on Wednesday we have our midterm exam. But I'll still cover some stuff in lecture, and so this week I just have this one slide deck, and we'll look at it today, and then we'll continue on Friday. And the topic is support vector machines, which like it sounds cool, right? As far as like, think of a cool sounding machine learning algorithm or something. You're like, support vector machines. That sounds really cool. It's, but the truth is, it's just drawing a line. So it's not that impressive. I mean, cool sounding name. But yeah, we'll take a look. We'll take a look at it. Okay, it's a classification method. All right, and we'll start by looking at the very simplest version of the support vector machine, which is what we call the maximum margin linear SVM, and that's literal. Yeah, it's just drawing a line. So the kind of the width of your margin is as wide as possible, the maximum margin. Okay, and that method works only for data that are linearly separable. Okay, and I'll show you some picture examples of it. And the idea is to kind of find these two parallel lines, or to generalize two parallel hyperplanes if you exist in higher dimensions. So, in 2 dimensions, you can basically have 2 sides when you draw a line, and then in 3-dimensional space, you draw a plane to kind of separate your 3-dimensional space into 2 areas, and then in higher dimensional space, you draw this hyperplane, okay? And that will separate 2 classes, and you'll kind of you draw kind of 2 parallel lines that are as far apart as possible. Okay, you want your parallel lines or your parallel hyperplanes to be as far apart as possible while still correctly classifying everything. And so we'll take a look. And again, when I do the slide deck, I can really only show you a 2-dimensional version of this thing. And probably in your head, you can picture a 3-dimensional version of the thing. And I think it's really hard to picture anything higher than 3 dimensions, but conceptually, the same idea also exists. So I'll start by showing just some examples that are linearly separable, and then once we kind of establish how that works, we can start moving into versions that are not necessarily linearly separable. Okay, so I'm going to just show possible pairs of hyperplanes, and the idea is we want to select the pair of hyperplanes or the pair of parallel lines to be the ones that are as wide as possible. Okay, when we see the parallel lines, the area in between them is the margin, and then there is going to be a line in between the 2 parallel lines, and that's it. Basically, you're going to see 3 parallel lines, and the one in the middle, that's going to be your boundary, is how we do it. Okay, so imagine I have these 2 clouds of points. I have the red points, which are shown with minus signs, and I've got the blue points, which are shown with plus signs. And can I draw a pair of parallel lines? Okay, and so if I were to draw a line like this, how far apart can I put the dashed lines? Okay, the dashed lines can be as far apart as this, right? So if this is my boundary and I have these lines parallel to it, how wide can I make it where basically everything is classified correctly? Everything to the right of this line is going to be I only have blue points to the right of it, and then everything on this side I only have red points to the left of it. Okay, now so this boundary the line in the middle will correctly classify everything in my training data. Right? If I say everything to the right of this boundary is going to get classified as blue, everything to the left of the boundary gets classified as red, that's going to be 100% correct. But the margin is, we would say, is not very wide. Okay. Now, if I rotate this, okay, we can see by rotating the boundary, right, by changing the slope of this, now my margin is a little bit wider. Okay, and I can kind of keep rotating and angling the boundary a little bit, and we can see the margin between the dashed line and this dashed line gets wider and wider, right? So this is narrow, this is wider, and this is going to be the boundary with the widest margin. And if I continue kind of rotating or changing the slope, then we can see the margin gets more narrow. Okay, so this is just kind of like, as I rotate this, it looks like, so we want the one that's as wide as possible. Okay, that's it. Okay, so this is our kind of set of parallel lines or parallel hyperplanes in higher dimensional space with the widest margin that are these two lines are as far apart as possible. Okay, and that's that. Okay, so SVM says the boundary that we want to pick is the one that maximizes the margin, that kind of distinguishes between one side and the other side, and says, this is the farthest distance. Okay, so the margin will be the perpendicular distance. Okay, so if we draw a perpendicular line to this, our margin will be basically from the central line to one of the dotted lines. Okay, and so we got a margin, same margin this way. So the width of, going from one dotted line to the other dotted line would be twice the margin. And that's what we have. And in our picture, okay, we have 3 points that are that define the boundary. Okay, so the closest points to the decision boundary, they will lie on the margin's edges. So we have 3 points on the margin's edges. Here we only have 2, but here we have 3. But basically, when we have kind of the widest thing that we can get, we have these 3 points. Okay, and you can think of 3 points as coordinates floating in space, but you can also think of points as a vector from the origin, right? And so we have a vector pointing to this this location, a vector pointing to this location, a vector pointing to this location. And so those 3 points are going to be called the support vectors. These are the support vectors because the margin, okay, this boundary here, is going to be strictly defined by these 3 vectors. All right, I could add more points. I could remove points. Any blue points on this side, and I can add or remove any red points on this side, and our margin will be unaffected. Okay, our margin, this boundary, it doesn't really care. It doesn't really care what where any of these points are, or where any of these points are, as long as we don't get any kind of points inside the margin. As long as these 3 points remain the closest points to the boundary, right? So measuring the perpendicular distance from this dot to the boundary and this dot to the boundary and this dot to the boundary, they're all the same. So these are the 3 points with the smallest distance to the boundary. These are our 3 support vectors, and it again, it's just kind of like these are your like 3 anchor points, or I guess they support the definition of this boundary. And we can add or remove points over here, and it really doesn't matter. Okay. All right. So they're called support vectors because you can change the location of the other data points, and the location of the boundary will be unaffected. Okay. Oh, this something happened with this picture. Okay. So anyway, here is the twice the margin, the distance between our two parallel hyperplanes. And these 3 points are the support vectors. And here is, twice the margin, right? This one would be a non-optimal boundary. We have a much smaller margin, much smaller distance between these two things. Okay, so the how do we figure out what our margin is and figure out our boundary? So we're going to do some math here, and we're going to start off with so let me just give you a disclaimer here. We'll start off with some concepts, and then we're going to get to a point where we just say, okay, we can't do any more math. We're going to solve this using quadratic programming, which I'm actually not familiar with quadratic programming. I've never actually carried it out myself. There's a little bit of like linear programming as an optimization method that I remember doing. Quadratic programming I've never done myself, but apparently it's there's computational ways to solve it, and you can do it kind of iteratively, and the computer will figure it out. So we're going to just get our math into this form that apparently can be solved via quadratic programming, and I just have to ask for your forgiveness for not fully exploring and trying to teach myself quadratic programming here. Okay, and I'm taking the notes. They're coming from Wikipedia and also our textbook here. All right, so we're going to start off with the linearly separable case, which is basically what we have here, where we can separate the two classes with a straight line, and we're not going to have any misclassifications, right? If you had like a different kind of set of points where there's overlap of things, you might not be able to draw a linear boundary that separates our two classes. But we're going to start off with the linearly separable case, and we're going to say we have our training data, which is a bunch of x vectors. Okay, basically the coordinates of all the points in your training data. Okay, you can think of each of these points as your input x vectors, and then all of them have a class label. In our case, they are labeled blue or red, or they're labeled with a positive sign or a negative sign. Okay, and so here the target label is either going to be a positive 1 or a negative 1, indicating the class. So we have two classes. One side is positive, one side is negative, right? And what we want to do is we want to find the maximum margin SVM that's going to divide the points, so that on one side you have all the positive cases, on the other side you have all of the negative cases. And we want to maximize the distance from the nearest points to that border hyperplane, right? So we're going to search for this line in the middle, so that the distance from each point to this line is going to be maximized. And in our case, we have these 3 support vectors, and all 3 of them have the same kind of distance there, right? So so that border is going to be defined by some vector w. Okay, so w is a vector that is perpendicular to that hyperplane, right? And we're going to try to find it where, when we do w transpose x, okay, minus some constant b, this is going to, and we set that equal to 0, that's going to define a set of points, right? So if you think of all of the x values that satisfy this thing, that's going to be the x values that lie along this line here, okay, or in higher dimensional space along the plane or hyperplane. Okay, so a hyperplane can be thought of as all of the x values that satisfy this equation, and our task is to figure out what is this w, what is this thing that's going to define the hyperplane. Okay, so if we look at the two hyperplanes, okay, the two parallel ones, this one, we could think of, so if this one is W transpose X minus B is equal to 0, right? We have another hyperplane where basically we're just kind of sliding it up or sliding it down, okay? This one we're going to define as W transpose X minus B is equal to positive 1, and this is W transpose X minus B is equal to negative 1. All right, so these are just hyperplanes that are parallel to kind of our solution. All right, so these are just, so this is on the positive side of the margin, and this is on the negative side of the margin. Okay. And we'll say we're going to just label the kind of the points that are the closest to that margin, that boundary, and we're going to label those x1 and x2. Okay, let me give you your first view quiz answer today, which is the letter C. C as in cat. C as in cat. Okay, so this is just kind of the same picture, but all labeled. All right, so this is our boundary. W transpose X nu plus B is equal to 0. And so, I don't have a good example, but let's just, let's say W is equal to 1 comma minus 1. All right, so this is not exactly it. All right, and so you could think of basically all of the points, and let's say B is equal to 4. All right, and so on here, I apologize. Here I wrote a plus B instead of a minus B, but it's the same idea. It's just a different sign for the constant here. Okay, and all right. And so if we want to say W transpose X, right? X plus B is equal to 0. All right, so you want to think of like, okay, what are all the points that are going to add up to this? And so basically I need W transpose X equal to, I guess in this case, -4. So I could have like -4 comma 0. And if I bump it to say -3, I would need like a -1. And then -2, right? Or am I doing this backwards? -4, 0. Hold on. Oh, I need this to be +1. Why am I having trouble thinking in my head? Yeah. Okay. Yeah. Yeah. Okay. This is working, right? All right. So these would all be solutions. All of these are x values. Okay. These would all be solutions to W transpose X plus B is equal to 0. I think. Okay. Because if I do this times 1 minus 1, we'll get -4. And then this times 1, yeah, okay. So all of these would be solutions to it. And you can see, okay, if I plot all these things, so this would actually be going in the opposite direction. But this would form kind of a line, or and again, in higher dimensional space, we would have some kind of hyperplane that exists. So anyway, that goes in the boundary. And then, if I change this to just say, okay, this is now going to equal to 1, all right, basically all of these things is just going to get shifted up a level or shifted down a level, right? So in our case, I would need -4 and 1, and this would become am I doing this right? I know I'm struggling with addition here. But basically we're just going to kind of either slide our line up or down if we change this, right? So we have W transpose X plus B is equal to -1, and W transpose X plus B is equal to +1 over here. Okay, and so So, you know, if you do have some new observation and it happens to be exactly on the boundary, then our result is 0, and it's not going to be classified as either plus or minus. But pretty much everything else will get either fall on the positive side or fall on the negative side. Okay, and in our training data, you know, we're going to have, you know, a margin between these two things. Okay, and so this purple vector, okay, which can be thought of as, let's take the vector, right? So we can define a vector as kind of like, what is the difference between this point x1 and this point x2? So I've got this this blue vector, and if I take the dot product, okay, with the vector that's perpendicular, okay, so a vector that's kind of parallel to this purple arrow, then we will get the distance, right? So if you take a vector and you dot it with another vector, you'll get the kind of its projection onto, you know, the distance that defines the projection onto that vector here. So here, this is what we have. So we're gonna that's what we're gonna do. So the margin, the length in purple is basically this vector x1 minus x2 dotted onto the vector w, which is perpendicular to the hyperplanes. Okay, so we're going to just say x1 and x2 are the closest points from the two classes. I could have also selected this one, and if I dot it to the to that vector w, I would end up with the same margin as well. Okay, so vector x1 minus x2 joins the points x1 and x2, and with the way we've defined the boundary, w is a vector perpendicular to that boundary. All right, and so we'll say w over the norm of w is the direction that's perpendicular to the boundary. The width of our margin is, again, we're going to call gamma the distance from this central line to the dotted line, okay, the perpendicular distance from this boundary to one of the parallel hyperplanes, and we'll call the total width from one dotted line to the other will be 2 gamma. And so I will take the dot product between, or the dot, or I can just do W transpose with this vector, okay? And we'll get the length of the margin. And so we want to find the W that's going to maximize this distance gamma here. Okay, and so if we say, so remember, we've got one distance over here, right? W transpose x1 minus b is equal to 1, and then x2 is on the other side, so W transpose x2 minus b is equal to -1, okay? Then I can kind of expand this out, and I'll have W transpose x1 and W transpose x2, and then I can kind of add a negative b and a positive b, and this is still equivalent, right? And then we find out, okay, well, this is equal to 1, and this is equal to -1, okay, with the way we've defined the locations of our boundaries. And then so we're going to get, okay, 2 gamma is equal to 2 over the norm of W, and so gamma is going to equal 1 over the norm of W here. So that's where we are, okay? All right, and so so gamma is in our denominator, and so now maximizing this distance here is now equivalent to finding the vector that's going to have the minimum norm, okay? Now, and we wish to minimize this thing, but this is going to be subject to the constraint, all right, that W transpose x minus b is going to be greater than 1 for all of the points that are labeled positive, and then all that's going to be less than or equal to -1 for all the points with the negative sign, okay? And we can kind of combine these two constraints into one constraint by saying, okay, well, let's take all of the points labeled 1, or all of the points labeled -1, and if we kind of multiply the sign by the solution to this thing, all of them have to be greater than 1. Okay, and so we want to minimize this thing, and it will share the same solution as minimizing this this quantity here. Okay, and that's just there just to kind of aid with the, I guess, the mathematical operations subject to the constraint, right? And so one way to solve for a solution where you're trying to find to optimize a function, okay, whether you're finding a maximum or a minimum subject to some kind of constraint, we can do this using Lagrange multipliers, right? And what we do is we're going to add a new term to the kind of the objective function for whatever constraint we have, so that the optimum of the new objective function corresponds to the optimum of the original constraint problem, right? We have n Lagrange terms. We have a constraint for every single point in our data set, because the constraint is that whatever boundary we pick, it has to put the point on the correct side of the boundary. Okay, so in our pictures, right? So the thing is our brains are really good at like looking at two-dimensional stuff, and we can say, okay, I would just draw a line right here. Okay, but again, once you start thinking in higher dimensions, it's really hard to kind of think. So you have to just make sure whatever line you draw, that this dot over here, this point over here, ends up on the same side as all of the other dots that are supposed to be plus, and the minus sign ends up on all of the things. Okay, so we have a whole bunch of these Lagrange terms, and yeah, so we got one for every observation. Okay, so our objective function is we're going to minimize, okay, this quantity, which can be expressed as W transpose W, okay, subject to the to a whole bunch of Lagrange terms. Okay, I've got this is Lagrange multiplier with this constraint. So I have this constraint, and this is that the classification of this point, is correct. All right. So so we have to make sure that that this thing is going to be this is going to work out. Okay, and then it says, unfortunately, there's no closed form solution to this Lagrange multiplier problem, but again, apparently it can be solved using quadratic programming. And again, I don't know anything about quadratic programming, but I guess it goes through and it looks at all of your x points, and and it tries to kind of maximize this. And a lot of what it comes down to is can we which of these kind of constraints can we kind of ignore? All right, because again, really the support, these three support vectors are really the only things that actually matter. Okay, once we figure it out, and the other ones, yes, they will get classified, but really it comes down to the 3 points that end up here. Okay, so again, we can add or remove points, and so here I just drew some extra blue pluses and red minuses, and I erased some. Again, our boundary is not going to change, right? So so one thing is that if this is what we want to minimize, okay, what we'll do is we're going to set the derivative of this with respect to W, and we're going to set it equal to 0, and then kind of solve for W. So we're going to get this into a form that can be solved by quadratic programming, and so this is what we're working towards. All right, so if I take the derivative of this with respect to w, I'm going to get, w transpose w will give me w over here, and then this whole thing, okay, so you have to kind of look at a alpha times t sub n times w transpose x will reduce to alpha tn xn, okay, and then these other things which are constants with respect to w, they just kind of zero out. So here I get this thing, and then I get w is equal to the sum of alpha times tn x, okay? And then if we, if we set that equal to 0 and solve, we're going to get kind of this. So this is what we have, and then to solve for doing the same thing, we take the derivative with respect to b. Okay, we get this this form over here. Okay. Oh yeah. Okay. I forgot this slide looked like this. So this just looks totally crazy, but this is the form that we can solve via quadratic programming. Okay, so we have this, and then we have this thing, and basically I'm going to just plug these back into here. Okay, so I have this part up here, w transpose w minus the sum of all this whole thing, and then so basically where I have w, I'm going to insert this back into it, and then where I have and then I also have this kind of term floating around. So anyway, plugging this back into where I see w, okay, I can do, all right, here I have the this w transpose w, and so this is weird, or it feels weird, but I'm going to have the sum over m and the sum over n, because this w transpose w, if we're going to treat it as kind of the sum of a bunch of x terms, we have to kind of take into account, like, x can go from, say, 1 through, like, if I have 3 points in my data set, okay, I want to take the product of, like, point 1 and point 1, point 1 and point 2, point 1 and point 3, and then point 2 and point 1, point 2 and point 2, point 2 and point 3, and then point 3 and point 1, point 3, basically every kind of possible product of all of these things. So this is why you see a subscript m going from 1 to n and a subscript n going from 1 through n. All right, so anyway, it all kind of gets multiplied, and we have alpha sub m, alpha sub n, t sub n, blah 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 blah. Right? It's just a nightmare over here. But if you look at this whole thing, kind of the terms end up canceling out with each other. So here I have the sum from 1 through n for alpha sub n, and then here I've got a w here, and then if I use subscript m from 1 through n, then because again it's just the combination of all possible basically elements in your thing, okay, then we get the exact same kind of product here. So this whole thing and this whole thing, they can combine, okay. I've got a 1/2 over here, and then I got a -1 over here, so I end up just getting a -1/2 of all of this. This whole thing, alpha and t and b, this is looking at over here, we know that this is going to equal 0 at the solution. All right, so this is going to end up being 0 times b, and then over here I've got a sum of the alpha n. So it's a mess. All right, let's not lie. All right, so this is what we get, but apparently we can solve this using quadratic programming here. All right, so it's kind of like looking at, basically we look at the labels of all of these different points. So we're going to look at every kind of combination of points. Looking at point 1 versus point 2 and point 1 versus point 3 and whatnot, okay, at their labels, and we're going to say, all right, we want to find basically find the optimum solution of this subject to this thing, okay? And the optimization problem doesn't contain W itself. So you can, again, kind of think of what this is working through. Here, let me go back. All right, so you have all of these points, and it's going to say, all right, it's going to look at this times, this cross this, and this cross this, and it's going to kind of look at basically from this point to all of the points, all of the other points, and really the only ones that matter are the ones that have kind of opposite signs. And it's going to kind of keep doing this until basically it finds like the ones that touch the boundary, right? It's going to say like, okay, these are the ones that are the smallest. These are the ones that have the smallest distance. If you're looking at all of the kind of possible kind of different points that you have in your x that are labeled positive and the x labeled negative, it kind of searches all of these kinds of pairs until it kind of finds the ones that lie along the hyperplane that end up being closest to each other. All right, and so once it finds those solution values for alpha, those are the ones that define your support vector. Okay, so at the solution, the support vector, the x points that define the margin, the ones that touch that hyperplane, will have alpha values that are not zero, and while everything else ends up kind of getting zeroed out. Okay, so the non-support vectors, the other points, will have basically no influence on this this boundary W. So it kind of looks at all of the the positive points, all the negative points, and it says, okay, let's look at this point to that point and this point to that point, and it goes through and it kind of finds, in our case, the 3 points that are along the boundary there, and it says, okay, these are the ones where we have an alpha value, and the W ends up being the sum of those things. Okay, and then everything else, it doesn't matter there. Okay, so here, let me give you your next view quiz answer, which is the letter B. B as in bear. Okay, so now we can think of alpha as a measure of how much influence a particular value in that training data has on defining W, right? And so right now it's just basically those 3 points. They each have, they're going to have, I think, an alpha 1, okay? And they define W, and then everything else has no influence. And so W becomes a matter of finding the correct values of this thing, okay? And that's going to give us this maximum margin classifier. So that's where we start. And then we want to start further modifying this, and so we have what's called the soft margin, and then we'll kind of expand, go from there. So the maximum margin classifier says, so I'm scrolling back here, okay? So it says, we need to find a boundary that's going to maximize the margin here. So again, kind of looking at all of these things, it's gonna find this one because it says this one draws the biggest boundary. Okay. All right. We can modify our constraint a tiny bit, all right? And we can say, you know what? We'll allow some points to be inside the boundary region, okay? So here, the value 1 represents the distance from that center line to the nearest point along the dotted lines. And we called this a hard margin because all of the data points must satisfy the property that that distance is at least 1, whatever margin we've defined. Okay. What we can do is we can put in just this term xi, I guess, okay? This xi term, and we can say, you know what, for some of our points, we'll allow the distance between x and the boundary to be less than 1, okay? So it just has to be greater than 1 minus xi, okay? So xi is some value between 0 and 1, so maybe it's 0.5. And we'll say, oh, you know what, for this point, we'll allow the distance between the boundary and that particular x to be only 0.5 rather than 1. Okay, let me see if, did I draw a picture of this? I didn't. So we'll zoom in. I don't know how to. All right, well, anyway, all right. So we said, all right, if I've got these, minus signs here, okay, and I've got these plus signs over here, right now we would define our boundary to be probably like this. This is what our thing, something like this, okay? Now, if I added let's say a minus sign right here, okay? If I added a minus sign here, now my boundary has to go like this, right? Using the maximum margin classifier. I'm gonna have to say, all right, this is my boundary, and this one point right here has a tremendous amount of influence on the line, okay? With the if I allow for a soft margin, this might not be a great example still. Basically, I will still allow some kind of line like this. So there's still some influence here, but we will allow this point to kind of still be within the margin here, okay? And we're going to say, so everything else has to be, they're not allowed to kind of enter this dotted line, but we're going to say, all right, at this point, this can be within the dotted line here, all right? So this distance, this one will have a distance of 1. We're going to say W transpose X minus B is greater than or equal to 1, okay? Multiplied by the sign T sub n, right? And then we're going to say, but you know what, this point, if we do W transpose Xn minus B, we're going to allow this as long as it's greater than, technically could even be negative. It could even fall on the wrong side of the boundary. As long as it's greater than 1 minus, whatever this xi is. Okay. So as long as it's greater than that, we'll allow it. Okay. And so that's going to be our soft margin here. So when using a soft margin, we're going to say, okay, well, we're going to kind of have this thing, but we're going to say, now there's a upper bound on what alpha can be, okay? We're going to have this a constraint, but alpha can't go over some value c, okay? It limits the amount of influence that a single point can have on defining the boundary. And so that's what we'll end up having, right? And so in this case, things get a little bit more murky because now, with the hard boundary, the maximum margin classifier, you'd really end up just having kind of 3 points defining your boundary in two-dimensional space, and then in kind of three-dimensional space, you could probably have just like 4 points. 3 points to define one of the planes, and then one to kind of define the location of the parallel one. But now you're gonna have kind of multiple values that get weighted with different kind of alpha things. So again, the solution can be done via quadratic programming, but it gets a little bit strange. The support vector machines, though, get really only become useful in classification problems by complicating our thing to allow for nonlinear boundaries. Okay, so all of our problems have used this quantity x transpose x, okay, xm transpose xn, and so we end up with this inner product. There is something called a kernel function that will transform our x values into a higher dimensional space. There's some we use the kernel function, and we'll get into this on Friday. But basically, this allows for us to have a non-linear boundary. Okay, so if we use only x transpose x and use that to kind of define this quantity, and we say, all right, we got to figure out the values of alpha to optimize this, we're always going to get these linear boundaries, which is fine in the simplest of cases. But in real life settings where your data is generally more complicated and not going to be linearly separable, then you won't be able to perform maximum margin classification. So using the maximum margin SVM, if you can't draw a straight line that's going to perfectly separate one side from another, you won't be able to use it. Okay, and so this allows us to have additional flexibility here, okay, by transforming our function using this kernel function. And so I'll get into this on Friday, but yeah, we'll transform the dimensionality of our product and allow work in a higher dimensional space, which then allows for when projected back down into either the two-dimensional or three-dimensional space, it ends up having what looks like a nonlinear boundary. It's a linear boundary in the higher dimensional space, but projected down, it's a nonlinear boundary. And that basically has allowed support vector machines to be actually a useful classification thing, because otherwise it's far too rigid to be able to draw these things. It just everything gets a little bit strange and wonky, and we start losing touch with reality. Okay, once you start doing these weird things, right? It's kind of like with neural networks. At a very basic level, we're doing these linear combinations of like our x and our weights, and we're just doing these matrix operations. But we've kind of abstracted it so much that we're not quite sure the meaning of any of the weights and things like that. And stuff like that happens when we use the kernel function here. So, in the beginning, we're like, okay, this kind of makes, I don't know if this picture makes any sense, but there's the idea of drawing two parallel lines to separate things, that makes sense. But then once you start projecting it into higher dimensional space using the kernel function, and then saying, oh, I'm going to draw these imaginary hyperplanes in higher dimensional space, like we can kind of conceptually accept that this is what's happening, but then when we think about it, we're not exactly sure. We just kind of have to trust the process or trust the math that, yeah, this is going, because at a certain point you're no longer able to visualize it, because the kernels actually will project our data into, well, depending on the kernel that you use, it might project it into this infinite dimensional space. And it's like, okay, you can't even imagine that. So, but I guess it works. Okay. But we have Friday. So we'll look forward to that on Friday. Until then, good luck as you study. Let me give you your last view quiz answer. Letter E. E as an elephant. And we'll call it a day here. And then we'll see you Friday. We'll just look at some pictures of support vector machines as it operates in this higher dimensional space. All right, we'll see you then.